Okay, so this is quiz number 25, and what we want to do here, you'll notice, is that we want to, find the load impedance. So if we put an impedance out here, ZL, we want to find ZL that maximizes the average power transfer. So the principle, if you remember back earlier in the semester, we talked about if we had a Thevenin equivalent circuit like this, RTH, VTH, and then, we added to this a load, RL. And the question was, so the voltage here is going to be VL and the current IL. The power through the load is going to be VL times IL. And the question was, what is this resistor R that maximizes the power transfer? And remember, the load resistance that maximized the power transfer was in fact the Thevenin resistance. Okay, so what we, the impedance that is going to maximize the power transfer when we hook this up is going to be the Thevenin impedance when we, think of the Thevenin impedance as looking in. All right, so we want to find basically the Thevenin equivalence of this circuit, and then the answer will be the load impedance. In other words, the answer down here, ZL, is going to be equal to ZTH, and then, so we need to find the Thevenin voltage and the Thevenin impedance. Okay, so what we're going to do is convert this circuit over to the phasor domain, and then we're going to find the Thevenin equivalent impedance. Okay, so let's just define a few things here. I'm going to define R1 is equal to 20 ohms, R2 is equal to 4 ohms. In other words, this is going to be R2, this is going to be R1, this is going to be C, so C is equal to 5 microfarads, and L is equal to 3.6 millihenries, and then omega is going to be equal to 5,000. And of course, when we go to the phasor domain, IG is going to be 3 phase of 0 degrees. Okay, so if we, we can think of the impedance. So ZL is going to be J omega L. ZC is going to be minus J over omega C. And we can actually go and compute these things. So let's see, I'm going to compute this using Python. So if I come, let's see, so if I have a little, see if I can make this work. All right, so I open up a terminal on my Mac, open up a terminal, and then I say IPython 3, and this basically gives me a Python environment that's kind of like MATLAB. It's just an interpreter. And I use NumPy, so I'm going to import the NumPy library as NP, and then I'm going to import the CMath library, which gives me, the ability to work with complex numbers. Okay, and then I want to define, let's see, R1 is equal to 20, R2 is equal to 4, C is equal to 5, 5 to the minus 6 farads, and L is equal to 3.6 to the minus 3 henries, and then omega is equal to 5,000. So ZL is equal to J omega L, and if I return ZL, so it's going to be 18. ZL is going to be 18J, and ZC is going to be equal to minus J over omega over C. And so ZC is minus 40J. Okay, so if I come back here, ZL is equal to 18J. ZC is equal to minus 40J. All right, so now let's draw this circuit in terms of the phasor equivalent. So I'm going to have a current IG, and then I've got R1. I've got my impedance here that I'm just going to call the impedance of the capacitor. It's going to be minus J over omega C. And then I've got an impedance of the inductor. Let's call that ZL. And then I've got a resistance R2. And I'm trying to find the Thevenin equivalence looking into this circuit like that. Okay, so this is going to be, I notice here that these two are in parallel, so I can combine those in parallel and then do a source transformation. So if I combine them in parallel, I'll get IG, and then this is going to be a new impedance. And this impedance, let's call it Z1, 2, let's call it Z3. And then I'll have, ZL and R2. And then this is still A and B, where Z3 is going to be R1 in parallel with ZC. Okay, and that's equal to, so let's come back, I'll come back here to my Python notebook and say Z3 is going to be equal to, so it's going to be, what was it, R1 times ZC divided by R1 plus ZC. So those are going to be those two in parallel. So it's going to be 16 minus 8J. So this is going to be 16 minus 8J. Okay, so now I can do a source transformation, and I'll get a voltage source and an impedance, Z3. My voltage source is going to be IG times Z3. And then I'll have, this will be in series now with ZL. And down here we have a resistor R2. And notice those are all in series. Okay, so this is going to be my VTH. And so in other words, VTH is going to be equal to IG times Z3, and IG is 3 phase 0, so IG is equal to 3 phase 0 is just 3. And so my V Thevenin is going to be equal to IG times Z3. So VTH, is 14 minus 24J. Okay, so I can write that as, whoops, what was it? 48 minus 24J. 48 minus 24J. We'll convert, that into phasors here in just a minute. And then I can, say that this is all actually equal to VTH, and then I'm going to have a new impedance, which is these other three impedances so this, we'll call this ZTH, AB, where ZTH is going to be the series combination of, these guys. So ZTH is going to be equal to R2 plus Z3 plus ZL. So we can write that out. R2, Z3, ZL. So Z ZTH is equal to R2 plus Z, Z3 plus ZL. So 10 plus, or 20 plus 10J, 20 plus 10J. All right, so there's ZTH, 20 plus 10J. VTH is going to be 48 minus J, 24. Don't know how that came out of my hand as I J, 24. And we can write this in terms of phasors. So if we look at the magnitude and the angle, so you come back here, so VTH, and then if we want to look at the magnitude, in Python we can use the absolute value for VTH, so that's going to be 53.67. 53, this is 53.67, and then we need to compute the phase angle. And so in Python I've got my CMath dot phase of VTH, but that when I do that, that gives it in radians. So I need to multiply times 180 divided by pi. Pi is in the NumPy library. So minus 26.6 degrees. And so minus 26.6 degrees. All right, so the load that maximizes the power is going to be 20 plus 10J. All right, so those are the answers. This would be the Thevenin voltage, Thevenin impedance, and then the impedance that maximizes the power transfer. Okay, that is quiz number 25.